at the 0 position at time 0. So that's the connection between Green's functions and the Dirac delta function. Or one of the connections at least. I think this is important to understand. I'm glad we did this today. So let's see, what does he say here? He says, however, due to the constant coefficients present in the, where is it? This equation, the response at t due to an impulse at t naught, g of t t naught is the same as the response due to an impulse at time 0. What? Well, anyway, there's something more to say. I don't quite understand that yet. I won't talk about it. Maybe I should try to talk about it. I'll try to understand it. Give me a second here. The convolution theorem shows that we're interested in q of, right, the q of t minus t naught, okay. I see why he says that, right? I also see why he's using t naught. Oh, isn't he sneaky? Because he wants to think of t naught as the initial time. Oh man, that's weird. Oh, sorry, it's weirding me out. However, due to the constant coefficients present in 13.36, okay. So he says G of t comma t naught is equal to g of t minus t naught comma 0. This is the translation property of the Green's function. Thus, q of t minus t naught is equal to g of t minus t naught. Therefore, through the use of the Laplace transforms, we obtained a representation of the solution of the non-homogeneous initial value problem involving Green's functions. Basically, he just says that you can call this g of t comma t naught, but the philosophy and reasoning for that is a little bit opaque to me at the moment, but that's probably just me. No, it's probably because we haven't talked enough about Green's theorem. We don't yet understand the entire idea here. The solution is the generalized superposition of all sources acting before the time t. It's an example of the causality principle for initial value problems, ordinary differential equations. In this form, the result appears quite similar to our results concerning Green's functions for boundary value problems, which we wouldn't know about. Blah, blah, blah. That is not at all what I intended to do, Cooper. What I wanted to show you, what I was planning to show you was one of these Laplace transform problems where we, you take the Laplace transform of a P, we still have a few minutes we can work out, right? We take the Laplace transform of a PDE, and you end up getting an ODE, which you can solve.
Using Laplace method?
Yeah. We're at FunQuest. All right, well, that seals it. I can keep talking. All right. We're at FunQuest. They went to FunQuest without me. How dare they? All right, so anyway, there's our introductory foray into Green's functions. I have like a 10-page PDF I wrote up when I was trying to understand this notion of Green's functions a few years ago. So maybe I'll try to get that to you guys and talk to you about what I learned there. It's related to what we just did, very much related. But anyway, so here's an elementary signal problem for a wave equation. Let's see, I think this is the kind of thing I want a simple one to do. No, that's not as simple. No, still not simple enough. Come on. You stupid thing. I want an easy problem. We don't have a lot of time. Jerk. Give me an easy problem. Come on. No, I don't want Fourier. I don't want the intersection of Laplace and Fourier. No, not what I want at all. I know the kind of problem I want. I can't find it. Give me a second here. Yes, I don't care. I mean, sorry. Yeah. Laplace transforms are awesome. They have many interesting properties, but how do you use them for a PDE? Come on. I want PDE. No, not ODE. PDE. Come on. You can do it. Here we go. Finally, I think. Tentatively hopeful here. So section 76 in Weinberger. All right, here we go. Partial u, partial t, minus partial squared u, partial x squared, aka heat equation, equal to 0. And it's unbounded, positive time. And, but we are given that u of x comma 0 is equal to f of x, and u of x comma t bounded. All right. He says, this problem was solved in section 70 by means of the Fourier transform with respect to x. We're now going to solve it by means of the Laplace transform with respect to t. Well, this is cool. Okay, so we're going to take the Laplace transform with respect to t. Laplace transform, partial u, partial t, minus the Laplace transform, partial squared u, partial x squared, right, equal to 0. Now if the Laplace transform, this is a Laplace transform with respect to t, right? So that means that the Laplace transform is with respect to t. I think that means that, it means x derivatives don't matter, right? Like, how would that mean? Well, he gives an explicit definition here. He says big U, big U of x comma s is equal to the integral from 0 to infinity. Ooh. Well, of course, e to the minus ts u of xt dt. All right. So, of course, by integration by parts, essentially, this piece, by the usual Laplace transform stuff, this is su, big U, minus u of x comma 0. But u of x comma 0 is f of x. All right? And then, on the other hand, if you differentiate under the integral, right? So, let's see here. Partial squared u, partial x squared is equal to the integral from 0 to infinity, e to the minus ts, partial squared u, partial x squared, dt. So basically the Laplace transform of the second partial derivative with respect to x of the time domain temperature function is equal to the second partial derivative with respect to x of the frequency domain temperature function, if you want to call it that. If you don't, it's too late. I already called it. Sorry. Partial squared big U partial x squared equal to a 0. All right. So that's he says for each fixed s, this is an ordinary differential equation. For u, x comma s considered as a function of x. In the place of boundary conditions, we impose the condition that u remain bounded for all x. He says the solution to this, then he just solves it. Okay. Okay, well, Okay, sure, fine. Well, this is not as much of a. I can't do much. I mean, I was hoping for these things where you can actually solve the problem by means that we know. Anyways, this is this is yeah, okay, fine. I mean, that's goodness gracious. Anyway, he claims that the solution is this. Golly, u of xs 1 over 2 times the square root of s, integral from minus infinity to infinity. Goodness gracious, e to the minus square root of s, absolute value of x minus y, yeah, f of y, dy. I mean, obviously, there you go. This can be seen. Well, I don't know. Apparently, you can get this by Fourier transform somehow. Interesting. So to actually solve the problem, we need to take the inverse Laplace transform of that thing. And holy moly. Just as an obvious extension as an analytic function of the complex variable sigma, the function is multiple valued. Choose a particular branch of it. Blah blah blah. The Mellon inversion formula gives you such and such. He draws a contour. He oh my goodness gracious, what have I gotten us into? Okay, after a page and a half of pretty serious complex analysis, we get to u of xt. This is not the example I was looking for. Sorry guys. 1 over 2 square root of pi t integral minus infinity to infinity e to the minus parentheses x minus y quantity squared over 4t f of y dy. Golly. So there you go. That's the solution. This agrees with the solution that we found earlier. Not us, but this book. Found earlier by means of Fourier transform. Gosh. Yowzers. Sorry, Cooper, I need to spend some time to understand the last 2 pages I didn't show you. It's page 356 to 357 in Weinberger's first course in partial differential equations with complex variables transform methods. Not kidding. Man. Alright, well anyway, it's a pretty good place to stop. So, thanks guys.